Hi, it's Dave. Welcome. Today I'm joined with James Douma, and we just recorded a part one about Tesla stock, TSLA dropping, and how James handles volatility and his long-term perspective. I thought it was a great episode. Check out part one. I'll go ahead and link it in the video description. In this part, we're going to focus more on Tesla's full self-driving. We're going to dive into certain specifics like what is Operation Vacation, how does Tesla do their pseudo lidar, approach? Like, are there any clever techniques they'd use? And competition. What happens if and when other competition or competitors catch up to Tesla's full self-driving approach? James, welcome to the show again. How have you been?
Great, doing great.
Awesome. So we've last week we talked about pseudo lidar. Do you have any more thoughts on kind of how we can explain how you can kind of crystallize, Tesla's approach to pseudo lidar? Why is it unique or different, and what exactly is Tesla doing to make kind of their approach? I wouldn't say comparable yet, but in a sense, by using depth and creating, these 3D, in a sense, bird's eye views, or almost in a way maps of their surroundings. They're overcoming some of the limitations of what maybe previously were thought with just cameras. They're going beyond that. So what are your thoughts on how Tesla is doing this?
Yeah, that's a pretty good summary of what you're saying. I thought that our previous conversation, like we covered a bunch of details, but then I realized kind of at the end of it that we didn't have a very good summary, like what should be the takeaway on this kind of stuff. And so there's two things lidar can be used for. One of them is knowing where you are in the world. That's called localization, and knowing very precisely. And then the other thing is it can be used to assist perception. Lidar, it can't be a substitute for cameras. As we talked about before, you have to have cameras. Cameras are just absolutely fundamental. They're going to be the core sensor that gets used in a driving system because of how driving works. That's just fundamental. What lidar can do, and this is one of the things that was a legitimate concern about Tesla's approach, is that it can facilitate your vision by giving you hints about things. But anyway, getting back to localization just to start with. So Tesla doesn't need localization. So their approach doesn't use HD maps. Having super precise localization is really important if you're using an HD maps approach. People who have already decided to put lidar on their vehicles, they tend to use HD maps because that leverages the lidar. They're already paying for it, right? But if you fundamentally want to do an approach that just works anywhere in the world, you can't do HD maps. And if you're not doing HD maps, then one of the biggest utilities that you get from lidar just goes away. So you lose all that kind of stuff. So then there's this second element, which is lidar can help make your vision better, right? So that was a legitimate concern because it was clear that vision systems that were augmented with lidar have outperformed vision systems by themselves. And the reason for this is that lidar gives a hint about what's in the scene by giving you a depth map, right? So it helps to separate objects from the background. And it also helps you to give a sense of the shape of objects, right? Like, if you to a 2D perspective, you see a truck from the side, you see a truck from the front, and it looks totally different. But somehow you have to know it's a truck, and you see it in 3/4 or whatever. You see a little bit of the front and the side, and then you see it in different lighting conditions and stuff. And all of those have to turn into truck, into the same truck. And so that's kind of a challenge, right? It's hard for the network to quickly and easily get the idea that this is a 3D object and I'm just seeing it from different sides, right? That's a stretch if all you've got is 2D data. Once you have the 3D data in there, suddenly it becomes a lot more straightforward because you're getting a shape go with the object itself, right? So a legitimate concern about using vision and not having lidar is that it would take significantly more data. I mean, one of the ways of thinking about this stuff is vision will eventually get it. If you have a billion pictures of the world, and I'm asking, the neural network to figure out about cars, eventually it's going to get, oh yeah, trucks are 3D things, and these are different aspects. And then it gets a lot better. Its accuracy improves a lot because it can interpolate between the two. It develops a space for that. if you give it lidar when you're training it, lidar data, it gets there faster. So it takes a lot less data to get to a particular level, actually. So what you could have said before as a criticism of using vision and not lidar for object detection or for perceiving the environment around the vehicle is that oh, it's just going to take too much data, right? You should use lidar because it's going to take way less data to get to acceptable accuracy. So, and one of the problems with trying to teach cameras about depth is that the main way that we train neural networks is supervised learning. That's the way most things that get deployed in the real world get done, which is basically, I've got this neural network. I'm going to put something in one end, and I want to train it to give me a particular thing out the other end. And the main way that this gets done is you take a bunch of examples where you've already figured out what the neural network should do. That's labeling, right? And you give it the example, and if it gives you the label, then it gets a good boy. And if it gives you the wrong label, then you give it a negative feedback, right? And what happens is once you give it enough examples, and assuming your neural network is big and the right shape and all that other stuff, but once you give it enough examples, they will figure that out, right? They just do. So the thing is, with depth is if you wanted to train it on depth using this trick, you got to give it a picture. And then the output is generally, it's going to be the same picture, but with a depth for every pixel. Like how far away is this pixel from where it is? And those are impossible to produce. Like you can't even produce those with lidar because lidar is not dense enough to basically give you a distance on every single pixel. So it was a big problem, right? It seemed like people who were just using vision, they were stuck with an approach where they just had to do like 1 billion images, or they needed vast amounts of data. And then there was the question about like, it could still lag behind vision augmented with lidar, right? So this is the super clever thing that we've got is Tesla basically figured out how to create a training mechanism that doesn't require you to label any data at all. You can just drive around and grab tons and tons of video. And they use what we call a geometric prior. Like you can, if you see the same scene from 2 slightly different perspectives, and the distances to the objects in the scene, the simple geometry of the scene tells you how it should look between the 2 different views, right? That's a pretty simple and straightforward thing. And there's a couple of corner cases about stuff that gets obscured. If a truck in the foreground moves to the left or to the right between 2 frames, right? Well, in one case, it's obscuring some part of the background. And in the other case, it's obscuring. So that's a detail that's got to get sorted out reasonably well. But the thing is, because we know how these things should move as the camera moves through the frame, what you can do is see if you use the neural network on the first frame and then you use it on the second frame, and then you look to see if it makes sense between the 2. Like, did the scene change the way it should have between these 2, which we know from the distances it said and what we know about the geometry, right? And if it does that, well, you give it good feedback. And if it does it poorly, you give it bad feedback. And this works, right? And the great thing about this is nobody has to label any data. Tesla can get they're drowning in data. They've got so much data from their thing. They've got this mountain of video data, and they can turn that into depth for these cameras, right? And once they've got depth, then all the benefits that you had with lidar before, they get those for free. They don't have to put a lidar on the car, right? So Karpathy showed this at scaled ML. So here's the important thing is that Tesla came up with a technique, and they didn't invent this, somebody else did. They adjusted it for their thing, and they've adjusted it in a very clever way that seems to be working really well for them. So not knowing this, you could have been concerned. Will Tesla get enough video data to get really good object recognition? Or will they be able to compete with people who are using lidar? Maybe not having lidar was a mistake, right? But now we know, basically, that they've got a technique. They can get depth. And we have every reason to believe that depth technique will work just as well as lidar does for enhancing the object thing. And now, so the one remaining benefit that they might have gotten from putting a lidar on the car is gone. Or alternately, what you could say is the concern that you might have had before about them not having a lidar, it's pretty much gone. And this isn't just Tesla saying, well, we have a technique. They showed some stuff that looks really good. And while it might not be perfect, the thing is, they're training it with an unsupervised method, and we know that they have infinite data. They got more data than anybody could ever use to do this, right? So they're going to get they've got enough data to make it as good as they want to do this kind of stuff. And so I feel like the takeaway is, okay, previously, not knowing this, you might have had some legitimate concerns about Tesla not having lidar for their business approach, because they don't use high def maps, right? And they don't need precision localization. But at this point, if you know that they can get depth with this supervised technique, and and they appear to be getting quite good depth, there's really no, I find it really hard to come up with an argument that's critical of Tesla for not having lidar at this point. And that's a relatively new thing. And so that was part of the takeaway that I was hoping people would get, and which I probably should have said more explicitly.
Yeah, no, that's great. Can you explain a little bit more in terms of how depth is calculated? So how dependent is it? I mean, it seems like one variable, one kind of input thing is multiple frames over a period of time, where, for example, the system guesses like that object is a certain amount away, and as it goes closer, it can either, it tests that previous guess, whether it's correct or not, and that trains the system. It seems like just the whole aspect of time and motion frames is one aspect, but then there also seems to be this aspect of multiple cameras having different angles. So how important is it to have multiple cameras? Can you do it with just one camera, or do you need two or three?
You can do it with just one.
And does it help a lot to have multiple cameras, or what's the impact?
It'll help. Yeah. I mean, it's going to be a benefit. So these two, they're kind of synergistic. You can do it with either one. If you have just static frames and just multiple cameras, because in a sense, the moving thing is, imagine that you're driving past a tree, right? You've got a background, you have this tree in the foreground, right? Mm-hmm. And so when you're driving by, what you see is the back, the tree moves, right? The background, if you're looking out the side of a car and you drive by, the background doesn't really move. The tree moves from left to right. And so you're trying to train the neural network to tell you the distance to the tree, right? And assume that the background is just pretty far away, right? Okay, so there's two things. You could have two cameras in two different places on the vehicle taking the photo at the same time, and the tree will move between them all two. This is just stereo vision, right? Or you could have the camera move. You take a picture, and then the car moves, and then you take a second picture at a slightly different place. So in a sense, they're both doing fairly similar things. They're basically showing you a very similar scene from slightly different positions, and you're going to try to correlate those two things. So having multiple cameras is one way to do it, and having a single camera over time is another way to do it. And each one, when you get into the nitty gritty about, getting all the details right on those two different methods, they have slightly different failure points. And so in that sense, they're synergistic. Like using both of them probably gets you a better result than using either one alone, where better result is you learn it with less data. So, instead of it taking, 1 million images, maybe it takes, 500,000 or something like that. It becomes more efficient. And maybe on the other hand, given a certain amount of data, you get better accuracy if you combine the two techniques. If I had my choice, like if I had to pick one or the other, I would rather have the cameras over time thing rather than the multiple cameras. And the main reason for this is Tesla's cars, they don't have 100% camera overlap, right? They have like 30% or 50% camera overlap. And that, I haven't done this experiment myself, but I suspect that introduces complications that are harder to overcome than the complications you get just with time. But I think they both have advantages and weaknesses, and they're probably complementary. And if you can do them both, then there's probably an advantage to that. But just using the tree example, right, to talk about what's going on. Say I have a neural network, right? And so, I've got my scene, I have my tree in the foreground, right? And I have my two pictures. One of them is from the car at one position, and then, because they get a frame every 30th of a second. So the car is like a couple feet, it's a foot farther to the left in the second photo or something like that, right? And the neural network, it looks at the scene, and let's say we're midway to the training process. And what I'm trying to do is it's guessing the tree at the wrong distance, right? So the neural network in one frame, it looks at the tree and says, I think the tree is, 30 feet away. and in the second frame, it looks at it and it says, oh, I think it's 40 feet away. And let's say the tree's actually 20 feet away, right? So one neural network, the one that sees that thinks the tree is 30 feet away, it guesses what the other one is going to see. Now, if I was this far over to the distance, well, the background is really far away, so it's not going to change at all. But that tree should move this much if it's 20 feet away, right? And so it's going to predict what the other camera should see. And likewise, the other camera can predict what the first camera can see, right? So if the tree is actually 20 feet away and one guessed 35 and the other one guessed 40 or something like that, they're not going to line up right. And that mismatch is going to be an error. And the more off they are, the bigger that error is going to be. So you can feed a signal back to the network during training and say, bzz, you got that wrong, right? And it'll relax on that thing. But on a different pass with a similar tree in a similar situation, if it made a better guess, it knows that those weights are closer to right. And so if you have enough examples on enough things, it figures out the distance because that error signal tells it when it's more right or less right, and it adjusts things accordingly. So it still takes data to do this. But the clever thing about the self-supervised thing is they have infinite data, right? They have unbelievably huge mountains of data because they've got 1 million cars out there driving around shooting frames at 30 frames per second. So they've got incredible diversity in their data. They have mountains and mountains of that kind of stuff. And if the technique works reasonably well at all, they're going to get good results out of it. Does that make sense?
Yeah. I mean, it seems, this would happen mostly, at Tesla headquarters, right? They would download a bunch of video clips. Yeah,
this doesn't happen in the car.
Yeah, and feed it into their neural net. Basically they're training their neural nets based off of all these video clips. But they've set up a system where they don't have to label it themselves. They're just feeding in these video clips. And the system is the neural nets are predicting all the distances and then seeing the errors. And then that's going back into the system to train the neural nets to make it better. So it seems like, there's no way Tesla wouldn't need all of the data. Obviously, they don't need thousands of clips for each car, on the road, because they probably, after a certain point, it would get pretty accurate. Is that? Yeah.
So when you look at the, accuracy, or let's say the error rate versus data, and you got a graph and this is 0, right? And so the more data you have, initially it drops really fast, so you look at your first, 100,000 and it's getting better really quickly. And then you look at the next million or so and it's still getting better. But then you get to 2, 3, 4, 5 million and the error is getting smaller and smaller, but it's going to start leveling out. There's an intrinsic error to pretty much anything that you do, an irreducible error where there's just a certain amount of noise that's fundamental to the problem itself. And you never get below that level of error. So what happens is it asymptotes to that. And then the question is just the farther you go on that curve, the more it costs, right? Because that's computer cycles. Like every single time you train the network, you got to go down that curve again. And so at some point you say, how much do I want to spend? Where's the point of diminishing returns? And typically you stop there, right?
Got it. It seems like based on Karpathy's talk, this was 10 months ago or so, in our last series, it seems like they've been doing this for quite a while. So, they're getting a lot of data. It seems like their depth kind of predictions would get a lot better. What does this mean? How important is this to the bigger picture of solving full self-driving?
So you need a certain level of object accuracy to drive safely in the world. And we don't know what the recognition accuracy that any of these people is getting because they don't publish that data. We can look at academic studies that are done on much, much smaller sets of data with a lot less resources. And we can kind of get an idea of what's possible with the level of resources that bigger organizations have. But we can't know. And at the margin, you frequently don't know if there's some problem that you can look at the curve and you can say, well, using this amount of data, we got down to, 0.5% error rate on this particular metric. And we think you need 0.1 to be able to drive in the world. Like you could do that thing. And you could look at that curve and you could say, well, then it would, on this curve, it would take this much additional data and computation to get to 0.1%. And we think that'll be good enough. So the two problems there. One is you actually don't know if the 0.1% is good enough until you put it in a car and go and drive it around, because the interaction between the accuracy that you have and the actual performance of the vehicle is very difficult to predict, right? And this is something a lot of these guys have discovered, where they looked at the thing and they saw how things were getting better, and then they went out and they drove it around. They're like, oh no, there's this other problem we didn't think of, right? So that keeps delaying the introduction of these technologies into the world. And then the other thing is, like, sometimes something happens when you're on the way to the curve between 0.5% and 0.1%. That's a little unexpected. So the only people who really know what's happening between 0.1 and 0.5 are the people who actually do that, have done that experiment, who can state with confidence. You can have a certain amount of confidence just looking at the earlier stuff and saying, well, it would take this much to get to that point. So that's kind of what we know. We know what academics have done. And we know, so we have a general, we being people who aren't actually behind, insiders in these organizations are doing this stuff. And probably my guess is that, Waymo doesn't know what Tesla's numbers are, and Tesla doesn't know what Waymo's numbers are for the most part, right? So there's a certain amount of speculation we have to do. The cool thing about the pseudo lidar thing and Karpathy's presentation on it was that one of the things that could have been a problem on the vision was, like, does it plateau? Well, I was talking about how it asymptotes. With the size of neural network that you can put in the car easily, will it asymptote to an error rate which is higher than is acceptable for driving? Like, that was a concern that you could have. Now, it's still a concern that you could conceivably have, because maybe even with lidar, object recognition will asymptote to an error rate which is too high. But there is a thing that we do know, which is, if it's working for people with lidar, it's going to work for people with pseudo lidar, right? So the scenario where, if, for instance, if you look at Cruise and you say, well, their system's working good enough, right? If Tesla can get to that level, they'll be okay. Well, right now, so with the pseudo lidar thing, you can remove lidar as a concern for why Tesla might not be able to do it. Does that make sense?
Yeah. I mean, so on the depth or pseudo lidar, would you say, would it be decently accurate way to look at it, where through Tesla's, depth recognition, they're able to mainly, do they translate most of that into the bird's eye view? Is that where a lot of that, accuracy is going to, where they're able to see the surrounding kind of map of what's around the cars more accurately? Therefore, they could have a more, better way to plan in terms of driving. And if that's the case, then is it bordering or crossing over to its own type of localization in itself, because it's in a way creating its own kind of real-time map? Let's say the bird's eye view gets better and better over time. So you're seeing your surroundings and you're seeing the location of your car in that kind of, real-time map in a sense. So in a way, is Tesla's vision approach kind of like almost creating its own, localized, I guess, surrounding map? And is that kind of the direction?
I think I might be miscommunicating something. Yeah. So the advantage of localization, like if you do high def maps and you do localization, is there are certain problems in driving that it solves for you that you don't have to solve by being more clever. And I think before I use the example of the curbs, you can go out and you can map where all the curbs in the world are, right? And the curbs don't move. So if you know where your vehicle is and you know where all the curbs are, you can absolutely guarantee, like if you know your vehicle, if you know where your vehicle is in the world to 3 centimeters accuracy, you can absolutely guarantee that you're not going to hit a curb, right? You won't hit a pole, you won't hit a wall, everything in the world that doesn't move. You just remove all those things from concern as far as collisions go, right? That's what you get with high def maps and localization. Now, it doesn't solve the problem for moving objects. So you could still hit a pedestrian, you could still hit a cyclist, you could still hit another car, right? But it does take a lot of stuff off the table that you might have to worry about, right? So if you don't use high def maps, you don't get all the static stuff for free. You have to figure out where the curbs are on the fly and where the walls are on the fly, right? And it's not going to, until your neural networks and your cameras are really, really good, it's not going to be as good as the high def map. So the thing about the high def maps is it's, I don't know, it's not quick or dirty, but compared to like doing it the hard way, which is building a machine that really understands the world really, really thoroughly, it's definitely less effort, right? So if you use high def maps and you use lidar for localization, you get this stuff and it's just solved, right? And now you can focus on other things, right? And so, you know, if you're developing a product and it's got all these things you have to do, being able to take a bunch of the problem off the table has a lot of merit to it, right? So that's one way of looking at what at the thing. Now, I think what Elon would basically say is, look, you have to be good enough to not hit cars and pedestrians. You just have to, right? And if you're that good, if you can avoid the moving objects in the world, avoiding the static ones isn't a problem, right? That's a much lower bar. So I think he would have argued that, you know, you have to solve this harder problem anyway. And if you solve this harder problem, the high def maps and the localization isn't really getting you a lot. It's getting you something. It's getting you some margin, but it's costing you too.
Sure.
Because you can only use it in parts of the world. You can't use it everywhere, right? So they're going to be, 99.9999% of the world you're not going to have a high depth map for. And that means your self-driving cars they're going to be stuck in a box somewhere.
I mean, I guess the question is, can neural nets and vision, let's say cameras, and can it get so good eventually, let's say 5 or 10 years down the road, let's say you have 1,000 times more powerful, engine, et cetera. Can it get so good where it's creating kind of that whole 3D environment around the car where having an HD map doesn't really give any benefit or much benefit because it's already creating all of the distances between all of the objects and really accurately.
It has to be able to understand the environment. I mean, in a sense, it's constructing this model of where it is in its head. So in that sense, yeah, it's creating a map, which the thing about the high def maps is they're crazy accurate, right? You don't have to be super, high def in the real world for most things, right? Like everything that's more than 20 feet away from you, you don't need to be, 3 centimeter accuracy, right? To it, right? There's kind of like this, a logarithmic requirement for accuracy the farther things are. And of course, there's a relatively small number of things that are really close to you. This is how humans do it, right? Like humans can drive cars and you're pretty good at telling, like if a pedestrian's in front of your car, you can tell where that pedestrian is to within a foot, right? But if the pedestrian's a block away, you can't tell where he is to within a foot. Humans can't do that, but it doesn't matter because whether it's a foot closer or farther doesn't affect what you're going to do. Right. And when it does get to the point where it's going to affect what you're going to do, it's close enough to you that right. So that's what you need to drive in the world. I don't need to know, exactly how far the post office box is from the curb, 2 miles down the road. I only need to know that, like if I'm driving up on the curb or something right now.
Yeah.
So high def maps, they solve a particular problem. And they solve it really well, and they solve it really efficiently. But that problem is a small subset of the overall problem of driving. And in a sense, the map of the world that a neural network can reasonably be expected to construct of its environment, it'll never match the high def map. But the places it won't match are the places that don't matter because they'll be the places that are far away from the vehicle.
Okay.
Am I saying that?
Yeah, that makes sense. With lidar, are there certain advantages though? For example, does it perhaps see better in dark, etc.? I mean, is that a concern at all?
No, not really. It's funny to hear people talk about the whole "what about in the dark?" Because we put headlights on cars, and they can see. Cameras see in the dark just fine if you add a light. A lidar is just basically it's got its own light, right? Is a lidar better in the dark? So lidars are a little bit better in the dark than they are in the daylight. If you could only see by headlights, right? If the headlight reflection was the only thing you could see with, driving around in the middle of the day would be tough, right? because everything is super bright because of the sun. The signal to noise ratio returned from your headlights goes down. And so one of the problems lidars have is when it's super bright outside, it can be challenging for them, right? They can also be, I don't know, I don't want to bang on lidar too much, right? It's a great tool. It's got a lot of super awesome uses, and the people who are using it in cars today, they're definitely getting value for it. And the main sort of thing that I thought was interesting to address in this context, where we're talking about is the fact that they're not using it. Like, is that a significant reason to be concerned about their ability to deliver on this in the long run? And I think we've seen enough evidence in the short run now that we can dismiss that.
I received an email from a viewer who is a software engineer, and he was saying that he thinks maybe Tesla should consider lidar. And so the viewer email was saying, periodically Teslas smash into large stationary objects while on autopilot because they don't see them. Because, for example, a turned over truck on the highway isn't in their training data with 100+ instances needed. That may be fine for Model 3, but will be very bad on Tesla Semi when it hits, for example, a school bus and kills people. So a few things about this. First, has Tesla solved kind of this kind of stationary object on the freeway issue that they had several years ago, where there were some instances where, a turned over truck or parked, something car, maybe the system didn't pick up on that and they crashed into it. Has that been solved recently or in the past few years?
We won't know it's solved until there aren't any more incidents. So the stationary object thing. So the radar that Tesla uses on its cars is a Doppler radar. And so it sends a signal out into the world, and it gets a return from everything. It bounces off of everything. And in Doppler radars, they discriminate different objects because the return signal that you get is slightly frequency shifted according to the relative motion of this thing. Okay, every stationary object it's at exactly the same frequency as every other stationary object, and the overwhelming signal return that a radar gets from the environment is at that it's at that stationary frequency. All the metal signs, all the buildings and bridges, like all the trees, the curbs, there's all this stuff which is super reflective, which isn't moving. So if you want to see a non-moving object using the radar, the challenge is dramatically higher than seeing a moving object is. Even if it's only moving like a mile an hour, right? All of a sudden it'll pop right out of the background because the frequency will shift. But an object which is absolutely not moving, it's still relative to the environment. Radars can see them. Like, radars are gradually getting better at doing this kind of stuff, but they're really poor at seeing things that are stationary relative to the background. And that's been true. So why isn't Tesla seeing these things, right? And so part of it is, before we were talking about how lidar can be used in combination with vision to make your object recognition better. And this is also true with radar. Radar can really help improve your object recognition, not just in training, but in the real world. So Tesla can basically take what they see in vision and what the radar is seeing, and they can use those two to cross-check each other. So in the real world, Tesla might have, they have a certain amount of confidence in what the radar is telling them in certain situations. They have a certain amount of confidence in what vision is telling them. And they'll correlate those two to increase the aggregate confidence that they have about whatever their perceptions are. And a problem with stationary objects is you totally lose the rate, because anything a radar tells you about a stationary object, it's going to tell you with very low confidence. So in that situation, you're just completely on your own with vision. And to the extent that radar is getting used as a crutch in certain situations, it's going to fail in the stationary object situation. So Teslas are going to be, to the extent that your vision isn't good enough to stand alone, where it really doesn't ever need the radar, the stationary object is always going to represent, a a vulnerability for the system as a whole. And it's especially going to be a vulnerability in situations where, for whatever reason, you are disinclined to trust vision alone. So an example is, if you see an object in a really unusual, from a really unusual angle, or in a real, something that just never occurs in your test set, your vision system might come back and say, I think that's a bus overturned on the freeway ahead of me. And I have 0.1% confidence that that is true, right? And your radar is saying, I don't see anything. It's wide open, right? Then you're in a situation where it's hard to make a good decision, right? Bird's eye view, camera synthesis helps a lot with this. And bird's eye view helps a lot with this. All these things that cross-correlate all the vision channels together are going to crank up that vision accuracy so that the dependency on the radar goes down and down. And ideally, it goes away. Elon suggested a couple of times that, vision is, you want to just be relying on vision. And you want to maybe occasionally rely on radar only in situations like fog, right? Like in situations where you've got this unusual condition occurring, and then maybe it's okay to rely on radar a little bit in that situation. But they have to crack the vision problem. They have to get it just completely nailed. And this is true, if that was a lidar, lidar's got a real similar problem, right? That there are times when your lidar, if you're relying on lidar to back up what your cameras are saying, and if the lidar says there's nothing there and your cameras are saying something's there, and you're going to go with the lidar in that situation because your vision isn't good enough, you're still going to hit whatever the object is that your lidar is telling you isn't there, right? And there are things lidar won't see. And something that's a really, planar glass surfaces, lidar is really bad with, right? So the surface of the bus isn't really a good example, but if you had an object that was tilted at an angle and it was really shiny and it wasn't in the object database or something like that, and so that your lidar is just bouncing right off at an angle, you get in a similar situation with lidar, right? And I think lidar is not so perfect that Google's out there driving with abandon any place that they went, because they know the lidar is totally reliable. They know that lidar has failure modes and radar has failure modes. And that's why these rollouts are slow. If lidar was perfect at identifying objects in the space, they'd have no risk of ever hitting anything, right? Because the lidar would be perfect. It would always tell you that something was in the way. But it does fail, and that's why these companies are slowly rolling these technologies out. Doppler radar has this giant blind spot for stationary objects, which is unfortunate. And I think the radars are getting better at dealing with stationary objects, but that's going to continue to be a problem to the extent that you are relying on radar to fill in the weaknesses of your vision system.
Yeah. Let's say there's this big stationary object, something on the freeway. Are the neural nets good enough where even though they can't necessarily identify exactly what that stationary object is, they could identify at least there is an object there, something to be careful over? Or do they need to have something in their, training set that actually they have to identify or correlate, that object to?
Eventually, they don't have to. Okay. So right now, neural networks, they're really good at finding objects that you have plenty of examples of. They're really good at that. And the development methodology for these things leans heavily on that. It wants to get a bunch of examples of everything to crank up that thing. There's a different sort of level of understanding your environment where you can understand there's something there and not understand what it is. And it's harder to get to that. It is possible to get there. And there are examples of systems getting there. And I'm quite confident that self-driving cars will get to the point where they will deal with objects in the environment that they've never seen. They have to, right? If we don't get that, then you're going to have these weird situations where some very bizarre object ends up on a freeway, and then a self-driving car doesn't make a good decision about it.
Mm-hmm. Yeah, definitely. Interesting. So I want to talk about Operation Vacation. So in Karpathi's last talk we talked about last week, he mentioned Operation Vacation. Can you explain kind of what that is and how Tesla is trying to use that, you know, to help their full self-driving program?
Yeah. So Operation Vacation is a comment on how Tesla organizes their autopilot team. So it's a very poorly kept secret that it's really hard to get ML engineers these days. Like if you're an ML engineer, you can make a ton of money in Silicon Valley these days. Like starting salaries are like $300,000. It's insane because these people are unobtainable. Everybody wants them, right? So a challenge that you have if you're doing a big scale effort is, well, I can't hire 500 of these guys, how do I make the best use of the people that I have? And Tesla's answer to that is they use the ML guys as a tool building team. So basically their autopilot team, you can think of, they've got this sizable team, and we don't know how big it is, but I guess it's probably several hundred or maybe a few thousand people, right? That are PMs, project managers, and labelers, and people who are basically turning the crank of like adding features into autopilot. Specing the feature, collecting the training data, testing the feature, collecting more training data to fill in the weak spot. That's turning the crank on the data engine that Karpathy talked about, right? And they've got this small core of really talented ML people, which might be, Karpathy talked about it being 30 people at one point and then 40 people. So it's like 30, 40, maybe it's 50 people now, right? But they have some space of people, which is tiny compared to the size of the team as a whole. But they want those people just working on the ML related problems. What they do is they have this team that builds tools. And they develop processes like, if you use this tool and you follow this process, you can train this algorithm. So they build tools for doing this training stuff. And then they hand the tools to the big team. And so the Operation Vacation is basically this goal that, like, if they're doing their job really well, because the tools should all be, you should have, if they're doing their job really well, there's a firewall essentially between the ML developers and the team. The ML developers, they get this set of tools working well, fully debugged, so they don't have to deal with any of this kind of stuff. They hand it to the development team and they can all go on vacation, right? And if they go on vacation, AP keeps getting better because all of the really hard, all the really labor intensive work, all the really time consuming work of making AP better is getting done by the team that's using the tools that the ML team is developing. So Operation Vacation is kind of a way of capturing the idea that if they're doing their job really well, if they all disappear for a week, nothing stops. It just keeps going.
Mm-hmm. Got it. Ultimately, I guess, we'll still need the ML engineers to continue to improve tools and get better, right?
And once again, I believe this is a goal. I don't believe they're anywhere. Because the thing is, like, ML tools with no bugs, give me a break, right? When the PMs are like, they're doing this thing, it doesn't make any sense, the tool is crashing, they have to call the ML team. They have to call the guys that wrote it, right? I think it's an ideal. It's not something that, But, if they could do their job ideally well and they're really, everything was going great, then they could. And I don't think they're there. And I don't think they're going to get there, right? Because their job is to keep pushing the envelope on those tools, right? And the tools are complicated and they're constantly changing them. You've heard how many times has Elon talked about rebuilding the stack, the training stack, right? The PMs and the labeling guys, they're not doing that. So.
Awesome. So what I want to do is, I have a ton of, so I think we've done some of our talk this week and last week on kind of the ins and outs of just current full self-driving. Actually, so one other question here is, Elon has hinted at a version 9 autopilot beta build, and there hasn't really been a huge amount of, let's say, updates. I guess there was a new update, 8.2 or something.
8.4.11 came out.
Yeah, right. This new version, Elon is touting version 9. I think he alluded it to be some type of dramatic change. What type of things would you envision? That type of a new version. Like, what are the improvements do you think that autopilot team is focusing on?
Yeah, that's So I only ever got to see one version of the FSD neural networks. On the AP neural networks, I often had a sense of how things were evolving because I'd see them from time to time, and you could see trends that they were doing, and you'd get an idea like what they were struggling with or what the arc was of what they were trying to do. On FSD beta, I only have one data point, so I don't know what the evolution direction is. Based on what, I mean, it seems pretty clear from what Elon has said that they don't have their stack fully. They don't have their labeling stack and training stack. And the stack that's all of the tools and the databases and the procedures that you use to ingest data from the real world and then use it to train the neural network and then pop out a finished neural network at the end. So there's all these tools in there, and there's the neural network architecture and the bits that go in the car and whatnot. So talking about the stack is just like everything from the input to the output. And for instance, when they started doing this self-supervised learning thing, which for training depth, that was probably a qualitatively novel element of the whole stack. And to incorporate that into the system, they probably had to change a lot of things in the overall software stack. So the day that they decided to bring that in, you can imagine they had some people working in the back and they had a couple of test mules driving around. Maybe it was some of those cars with lidar on it where they were A/Bing it, against test data and that kind of stuff. And they get to a point where they're confident the technique works. Some guys go off in one room and they write all the stuff that they think it takes to get that integrated, right? And so there comes a day when you have to merge that into the stuff you're doing in production, right? And what happens when you merge when you make big changes in a production is everything breaks, right? And then so the whole system is basically down while you figure out what's wrong and patch all the bugs and make all the changes and that kind of stuff. And then when you get to the end, you have to validate that it's working, and then you crank some data through it. So you build the first couple of generations of the network. So you get these breaks when you introduce a significant new sort of deviation from the MO that you've been using. And I think it's almost dead certain that they're introducing some structural change, which is probably invisible externally, but which as a user, you would just experience it as, wow, it suddenly seems to be working better, right? Because the accuracy's got significantly better. They'll find some source of error in the system and they'll make a discontinuous change. And then there will be a category of errors that the system was making before with a certain frequency, and that frequency will decline significantly. And then over time, they will gradually rewrite the code to take advantage of that. Like if you have an error that occurs at a certain frequency, you have to have stuff downstream of that perception or decision process that catches the error and fixes it. Or you have some way of kind of dealing with that possibility. Back on AP1, for a long time, they had this they had the vanishing horizon problem, which I unfortunately got enormous amounts of experience with, because I was trying to figure out how to solve it myself. At the same time, I was constantly experiencing it in my car driving back to San Francisco. So I had mapped out, like I knew every curve between here and San Francisco and exactly where the system would fail. And as it got better, I was watching it and I was watching the error asymptote to a completely unacceptable level. Like they weren't going to get there. They really needed to do something different to do it. And then then they had an update. It was a highly anticipated update. I think it came out in March of 2018, and we didn't see anything for a long time. And they came out with that update, and boom, the horizon problem was just gone, right? So they had been working on this problem with the horizon problem is you're driving along a road and say the road's got some rises and dips in it. And of course, if you're driving up the Grapevine, from San Francisco to Los Angeles, there are lots of places where, the road lumps and on a curve, right? And so, at that point, autopilot was choosing its path by looking at the lane lines mainly. And it still uses lane lines to a large extent. But, it sees the lane lines going and they just end at the top of the curve, And of course, as you get up there, you can see over the curve and you can see where it goes. And as a human being, you can see the line of trees or whatever on the roadside. So you have a sense of where the thing is going. But autopilot really cared a lot about the lane lines at that point, right? And as you would be cresting that hill, you would feel the steering wheel would start jiggling, because as that line's getting shorter, it's getting more and more uncertain about what happens over the top, right? And occasionally you'd get to the top of the hill and the error would like go to infinity just as you were cresting the hill, and then the steering wheel would do something wonky, right? So it was a known failure, and I experienced it tons and tons of times. So Tesla had various things in the pipe for dealing with this failure mode. And the one at the very end was they had this rule, which it was like, depending on how fast you were going, the car wasn't allowed to turn the steering wheel more than a certain amount, right? So if you were going 70, they'd look at a road, 70-mile-an-hour roads. This is as fast, as tight as the curb can be. And they had a hard limit. It's not allowed to go any tighter than that. And so by setting that hard limit, they avoided catastrophes on that hill cresting problem, which was just happening all the time, right? But now there's a downside to having this thing, right? Which is, say you're driving on a perfectly flat, reasonable road in LA, like you're on the 210 freeway. There's sections where the 605 merges, and it's got a couple of relatively tight curves there. And you're in a zone where the speed limit is 65 and there's a certain curve, right? But everybody's driving 75, right? And you want to keep up with traffic. So you'd get this thing where the car couldn't turn the wheel enough to stay in the center of the lane at 75 on a 65 road. And so, there was a super common experience that you would have on freeways is like, if you're in the fast lane or you're keeping up with some of the faster traffic, you'd hit a tight curve, the car would slowly drift to the outside of the lane, right? And then at some point the curve would end and hopefully you'd still be in your lane when it did, right? And then it would get back to so the cool thing was they had this thing well downstream with this very simple rule, which was super safe, which is you can't turn the wheel harder than this, right? But then it has these consequences in these corner cases where like you're in LA and everybody's driving 20 miles an hour over the speed limit, right? And you get these other failure modes that go. So one of the ways that we experience stuff getting better is as the accuracies get better, like when that cresting hill problem went away, that couldn't stay in your lane on the freeway problem went away too, because they could get rid of that downstream rule. They didn't need it anymore to protect you from the vanishing line thing. And all of a sudden, all these problems got a lot better. There was this rare thing, which was the hill cresting problem, and not super rare, but it only happened in certain situations. But the side effect of fixing that, in a super trustworthy way in the cars was that it caused this other problem that was really common. Because if you're in LA, everybody's always driving faster than the speed limit, right? So you always had this problem with the car drifting out of the lane. Mm-hmm. Anyway, and so my guess is, the experience of these long delays in autopilot is, they make steady progress and then they have a gap. And they come back from the gap and you get two things. One big class of problem is suddenly solved. And there's like 10 little bugs, so it'll, because they just merge this big thing in. And then over the next, 2 or 3 point revisions or 5 point revisions, the bugs gradually go away. And at the tail end of that process, it's significantly better than it was before. And I've been driving autopilot since the very first version. And I've seen that, them go through that cycle, 15 times or something like that. So this will be another one, I think.
Yeah. Interesting. Elon Musk noted that I think Q2, he was saying that they're going to launch monthly subscriptions for full self-driving. What do you think that means? Does that mean that it's going to go out into beta or wide release for full self-driving if there are subscriptions, or what are your thoughts?
Well, we'll have to see. I don't know how many core problems they have with FSD right now. It could be that all of the major interventions they have trace back to like 1 or 2 core limitations that they're experiencing, and they might be really confident that if they have a definitive solution to those, that the system will be performing significantly better, and maybe they can go into wide release. The discontinuous improvements are really hard to. That when they're in that zone where they've just got the little point improvements, which sometimes goes on for a couple of months or something like that, after the first couple of point improvements, you can watch it improve. Like it'll all the little things that are annoying you will just gradually get polished up so that it gets better. And then you get this discontinuous change. And there have been 2 or 3 discontinuous changes where like it got so much better. It improved so much more than I expected it to during that discontinuity. Because of that experience, I'm super reluctant to try to make a prediction about how much better it will be after the next discontinuity.
Yeah.
I mean, my general feel about the arc of this thing, although, I would have said the same thing a year ago, so that gives you a sense of my accuracy, is that, yeah, they're like a year away from being able to give it to people, being able to roll FSD out to a decently sized population of people, with the same caveats that they have on the autopilot. You have to, you have to be paying attention. Mm-hmm. You're still in charge of the car. It's not taking over for you. I think they're like a year from doing that. And I think that's a year from it being really good to where, a year after that, you get to a point where you could take a nap. It wouldn't be smart. You shouldn't do it, but you'd probably be fine, right? And a year after that, they'll have collected enough data that they'll be able to convince regulators. And so that's kind of what I think they have to have a really good system in the field for a year before they've got enough data to convince regulators that it's good. And I think that having that system be really polished is going to happen like a year after they get the first version into wide release. Like that's the time scale that I'm expecting.
So you're thinking 1 year to get to really decent wide release condition, but then another year for it to get pretty good, really decently good, and then a year after that to get regulatory approval.
Oh, that's the scale.
Generally,
right?
But of course, everything is.
But yeah. So I look at it like I'm not expecting robotaxis in 6 months or 12 months. I'm just not. Like I don't see that really happening. Like if everything went super, super well, which is certainly possible. Like I've been surprised at. I'm constantly surprised at how much better it gets. Yeah. They could have a really good system in a lot of people's hands. In 12 months or something like that. Yeah. That's kind of what I expect. But, there might be something that I don't know about that they're going to roll out on the next one and bam, they got it. Those things happen. They do. It's just, externally, you just can't predict because the shape of the improvement curve is like, but don't, and occasionally it's a really big step and we don't know where the end is. I think even Tesla doesn't know where that final end is. That's why you put it in the hands of a lot of people and you have them go drive it in the real world and you get 1 billion miles of statistics. And once you've got that 1 billion miles of statistics, at that point, Tesla can be super confident about how it will perform if they just let people go hog wild on it. Right. But until you've got all that data, they don't know, right? They can have a good feeling about how things are going, but they can't know until they've got that data.
Mm-hmm. Awesome. I want to go ahead and wrap up this episode. In our next episode, which we'll record just in a few minutes, I want to go into Tesla's competition. Can competition catch up? Are there, what does it look like maybe 5 or 10 years down the road? Are there any inherent advantages maybe Tesla has over its competitors long term? But I want to dive into that. We might touch also into kind of what full self-driving is worth. We might push off some of that discussion to the following week, because I think that's a fascinating topic because it deals with so much in terms of, possible, revenue, opportunities, and just business model, etc. So let's go ahead and we'll wrap up this episode. Before we close, for any of those listening, watching that want to get more into full self-driving, understanding the basics, I've created a James Douma playlist on my channel. So I'm basically putting all the interviews I'm doing with James Douma into this playlist. So you can go ahead and look and watch all of the interviews.
Highly recommended for insomniacs.
You can watch all of the interviews from the first one, so you can get a foundation. So the more you watch, actually, the more some of the stuff I think gets more familiar, and it starts to unlock some clarity with this whole thing. So anyways, we'll see you guys in our next episode. Thanks.